everyone, welcome back to our physics video series. Today we will be discussing about one of the most iconic experiments of physics, and those are the Young's double slit experiment and diffraction grating. Before we delve into the experiments, we need to first understand a concept of waves behavior, and that's called interference. What really is interference? Interference usually happens every single time around us due to the wave's behavior. Now, when two or more waves are going to come from opposite ends, and if the waves are having same frequency and they're having same phase difference, as in they're coherent, and also having same amplitude, if the waves are emerging and meet at a point where the crests are aligning, they will superpose and the amplitude will add up to form a constructive interference in the crest side and also in the trough side. However, if they move a little more and the crest is aligning with the trough, they will have destructive interference, as in the displacement will be cancelled each other out because of equal magnitude of amplitude on the crest side and the trough side. As a result, we'll have a destructive interference. Now, a series of constructive interference and a series of destructive interference are called maxima and minima respectively. Now, when a light that is monochromatic here means a light having single frequency. When a monochromatic light is focused from one side of the double slit, the waves try to move through the slit. Now, since the light waves are moving through the slit, they are diffracting. As they diffract, they spread into geometric shadows. Now, when they're spreading like that, their wavefronts are in contact with the other. So wavefronts are made up of series of crests and troughs, by the way. So when the wavefronts are interfering, the crests and troughs are interfering. So when the crests are interfering with the crest, they're forming constructive interference. When the crest is interfering with the trough, it's forming destructive interference. Now, as there are so many wavefronts and there are so many constructive and destructive interference, they're going to form series of maxima and series of minima. Series of maxima are the position that can be seen in the screen right next to the double slit, parallel to it. You'll see it on a screen that there are bright fringes coming out. If you're using, let's say, a red laser light, you're going to see red bright spots. Those are called the bright fringes. And you're going to see some spots in between that are going to be dark, and those are called dark fringes. Now, bright fringes that are appearing at the very center is called a central maxima. Central maxima happens to be the most intense interference. It has the highest intensity. And the intensity gradually keeps on decreasing order as you move away from the central maxima. Now, why does that happen? This is a very frequently asked question, that why does the intensity keeps on decreasing if we move away from the central maxima? Now, the thing here is that as the wave train are kind of interfering, the wave train is interfering in a very different way in every point. How? Because imagine the central point, the central maxima that we're talking about right now. The wave train coming from the slit number 1 is interfering with the wave train that is coming from the slit number 2. The phase difference between the two wave train that are coming to meet at the central maxima is usually same. But as you move away from the central maxima on the screen, the wave trains are having different journeys. As a result, the phases are having variations. When the phases are having variations, the intensity kind of decreases. That's one of the reasons why. This image right here shows us a demonstration about how the double slit experiment really works. Now, in the double slit experiment, right in this one, we're using a single slit rather than a double slit at the very first. The reason why we are using it is because we want to make the sunlight that is entering the slit to be coherent. To draw in coherent sources, we will be using single slit. As the coherent sources slowly comes in contact with a double slit and they go out from double slits, they diffract into geometric shadows, as you can see it here. The red one shows the crest, the yellow one shows the trough part, and these are all wavefronts. Now, as we know about interference pattern from our earlier video, that when crests meets with the crest, it forms a constructive interference at the crest side, and then trough meets with a trough, that's also constructive interference at the trough side. But if a crest ever meets with a trough of equal magnitude, they're going to cancel each other out. But if it's not an equal magnitude, there will not be zero displacement. There will be some displacement. So you have to figure out depending on whether they're of equal magnitude or not. All right, so now when the waves are meeting, for example, this position, the crest meets the crest, crest meets the crest, crest meets the crest. These are all your constructive interference. Now, series of constructive interference can be projected on a screen to show a bright fringe right here. It's called bright maxima. And you will not just find one bright maxima, you're going to find a lot of bright maxima. But as you move away from the central maxima, as you can see, the intensity slowly fades out. The reason behind that is intensity depends on two things, the path difference and the phase difference. So at this point, let's say what's happening is, I'll try to make a difference between point X and the central point. Let's say you have two sources right here, and this is the point X. Here you have a bright fringe. At the very center, you also have a bright fringe. Now at the very center, what's happening is the wave train coming from slit number 1 and the wave train coming from slit number 2, they have zero path difference between them, as in they're exactly like one another. So, and they don't have any kind of difference in their phases or paths. So they are of equal in length, equal in angular displacement or path difference, and as a result, they're overlapping and forming an observable bright fringe that's very bright because of the intensity, because of its proper overlap. But if you move away from the central maxima, what happens is the wave train that is coming from slit number 1 and the wave train that is coming from slit number 2 right here, they have some kind of difference between their length of the path they have traveled to reach there. So this difference between them causes them to have a path difference. If the path difference usually is of an integer variable of lambda, usually you get bright fringes right here. So, but the bright fringes are not as much sharp as of that of the central bright fringe. That's because they have variation in their phases. The waveframe that was entering to be at the central maxima, to cause the central maxima to happen, they didn't have much difference between them. So the reason why we have difference in intensities as you move away from the central maxima is due to the path difference and phase differences along the length of the your screen. And the more wider the screen will be, the more it will be distributed, the more length the waves have to travel to meet at a certain point, and therefore more fade out it will be. So therefore, you get the brightest at the very center, the next brighter will be at right adjacent to the center, and then it's going to fade out. Now let's consider a wave train entering slit 1 and slit 2. They undergo diffraction and then they interfere with one another, forming series of constructive interferences and destructive interferences, resulting into bright fringes and dark fringes on the screen. Now, we are here to derive the equation of the Young's double-slit experiment. Now, let's consider a scenario where a wave train that is coming from slit number 1 happens to travel some lambda distance to point P right here. Since I have mentioned that they have traveled some lambda distance, this length right here is called the path length taken by the wave train. Now, the path length taken by the wave train from slit number 2 seems a little longer, which it is, happens to meet constructively at point P again. And since they're meeting constructively, they form a bright fringe. Now, we will be assuming that this length right here from S1 to P, the path length right here, is a little smaller than the path length right here. You can really observe it and say that, right? Now, we are assuming that there's a point X, which tells us that the path length taken from here to here and from X to P is exactly the same. That means the extra distance traveled by the wave train coming from your slit number 2 is basically right this position right here. That is X till S2. Now, let me remove this entire thing right here. So what we're trying to say is the path length traveled from S1 till P is the same as the path length traveled from X till P. So the extra distance, the wavefront that traveled from the slit number 2 had this length with it. We'll call it and represent it with the letter del lambda. Let's consider the fact that the angle with which the wave plane deviated from the horizontal is theta. This angle right here is the same as the angle right here. Now, in order to derive it, we will be using some symbols of the experiment. Now, the difference between the slit 1 and slit 2 is represented with the letter A, and we call it the slit separation. And the difference between the right fringe to right fringe or dark fringe to dark fringe is represented with the letter X. That's fringe separation right here. The separation between the screen to the two slits is represented with the letter D, and that's a screen to slit separation. Now, let's consider the bigger triangle right here first. In order to resolve it, we will be using trigonometric expression tan theta. As you guys already know, the tan theta is opposite by adjacent. The opposite side of this angle is X, and the adjacent side is D. And now let's resolve the smaller triangle right here. Now the smaller triangle right here can be resolved using sine theta. Sine theta is basically opposite by hypotenuse. So opposite side is del lambda, and hypotenuse right here is A. Now, one of the assumptions in this experiment is that this screen right here has been placed at a very far distance, and when you do so, this line S2 till P and S1 till P happens to be very much parallel to one another, which makes this angle very small. As this angle becomes very smaller, we can write here that sine theta is approximately equal to tan theta. When that's the case, we can also say that lambda by A is actually equal to X by D. Here you go. Equation right here, lambda is equal to XA by D has been proven and derived. Thank you for joining us in this enlightening journey. We encourage you to delve more into physics and its wonders. Please don't forget to like, share, and subscribe. And until then, keep learning and keep exploring.